Namaste. Welcome to the Indian Knowledge Systems Primer Course for Children offered by Anaadi Foundation. In this Bharatiya Ganita lecture, we will look at magic squares. As we have seen in our previous videos, Narayana Pandita's classification of magic squares tells us more about what are these different types and how do we construct them. So, based on the order of the magic square, Narayana Pandita classifies magic squares into 3 types in his Ganita Kaumudi written in 1356. From the verse which we heard before, we find that there are 3 types. These are Samagarbha, Vishamagarbha and Vishama. When the order of the magic square is divided by the number 4, if the remainder is 0, then it is a Samagarbha. If the remainder is 2, it is a Vishamagarbha, and if the remainder is 3 or 1, then it is Vishama. The objective of Narayana Pandita's classification of these magic squares is to enunciate and give us the techniques for each of these types. These techniques revolve around the construction of these magic squares. So, magic squares whose order is an odd number are called Vishama. Remember that we cannot construct magic squares from 1 or 2 and therefore we begin with the number 3. The magic squares which are 3 cross 3, 5 cross 5, 7 cross 7 etc. are called Vishama. Magic squares whose order is a multiple of 4 are all called Samagarbha. So, these examples would be 4 cross 4, 8 cross 8, 16 cross 16 and so on. Finally, magic squares whose order is an even number that is not divisible by 4 are called Vishamagarbha. The examples of these would be 6 cross 6, 10 cross 10, 14 cross 14 and so on. So, these are the 3 broad classifications of magic squares we find in Narayana Pandita's. Another way to classify magic squares is such. Depending on the number of variant ways in which one can get the desired sum, magic squares have been classified into the following 3. First is a semi-magic. A semi-magic square is where only the rows and columns sum up to our magic sum number. In a magic square, our rows, columns and our principal diagonals add up to our magic sum. And finally, this special category called a pan-diagonal magic square, in which all of the above plus the broken diagonals also give us the magic sum. Let us see how. So, on the screen here towards the left, you can see a magic square where the sum is 34. So, 12 plus 3 plus 6 plus 13 will give us 34. 12 plus 14 plus 7 plus 1 will also give us 34. And similarly, if we add the diagonals, that is 12, 5, 9 and 18, the sum will be 34. However, if you were to look at the broken diagonal, here marked in the blue color, you will see that the sum of 7, 5, 6 and 8, right? If we were to extend this diagonal here and wrap it, we would get the number 8 as a part of this diagonal. We realize that the sum of this diagonal or the broken diagonal is not equal to our magic number, which is 34. This is why the figure on the left which you see, this is a normal magic square, right, with the magic sum of 34. Now, let us look at the third category or our special category of a pan-diagonal magic square. Now, what is a pan-diagonal magic square? In a pan-diagonal magic square, apart from the rows, the columns and the principal diagonals, here the principal diagonals will be 10, 16, 7, 1 and 15, 9, 2, 8 as you can see. Apart from these rows, columns and the perfect diagonals, broken diagonals will also give us the same magic sum. In this square, the magic sum is 34. Now let us try picking a broken diagonal and seeing if we get the same number. So let's start adding this broken diagonal marked in the yellow color. So you will see 4 plus 16 plus 13 plus 1, which is wrapped around here at the bottom, gives us the sum of 34, which is our magic sum. Similarly, let's look at the pink broken diagonal. 5 plus 3 plus 14 plus 12 also gives us the magic sum. This figure on the right is a pan-diagonal magic square, where it has extra properties from our normal magic square, which we see on the left hand side. Now, as you can see on this slide, there are 52 unique ways to sum pan-diagonal squares, and these are marked in the yellow in each of these cases, as you can see in front. So, the rows, the columns, specific grids of 4 quadrants that we are able to pick here, right, as you can see. So, these 52 unique ways of adding will give us the same magic sum, making it a 4 cross 4 pan magic square. Now, let us look at Narayana Pandita's Turagagati method for pan diagonal squares. An ingenious algorithm to build 4 cross 4 pan diagonal magic squares has been given by Narayana Pandita in his Ganita Kaumudi around 1356 CE. Turga means horse and Gati means motion. This method employs the horse moves on a chessboard to place numbers relative to each other in order to construct pan diagonal magic squares. Narayana Pandita states that using this method employing 16 numbers in an arithmetic series, these can be 4 sets of 4 numbers in arithmetic series, with the first number of each set in arithmetic series with respect to the other, we can produce 384 possible variations using the same 16 numbers. Subsequently, we will see how. Now, let us dive into Narayana's Turagagati algorithm. The sequence S that we choose for demonstration is as follows. So, S equals to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16 as the numbers we will use. Now, once we have our sequence ready in place, we create 4 subsets out of this sequence. Let's look on the screen what these subsets look like. So, our first sequence is a set of 4 numbers. For the application of this method, it is important that we clearly write down and create these 4 sets. The horse moves that will be considered for obtaining the magic squares are represented in the following way. So, H1 will be 1, 2, 1, 3, 3, 4, which means that each of these numbers written within the smaller bracket must be placed at a horse move from one another. The second will be 5, 6, 5, 7, 7, 8. Third will be 9, 10, 9, 11, 11, 12. And finally, our fourth horse moves will be 13, 14, 13, 15 and 15, 16. The transition between these sets must also be a horse move. Let's see how. Which means 1 and 5, which is the first digit of H1 and H2, 1 and 9 and 9 and 13 must also be at horse moves from each other. Here you see a pictorial representation of how these horse moves must look like. Now, let us try looking at different horse moves and how we can see number placement through them. As you can see in front of you, there are 4 squares. We will try figuring out through horse moves. let's say in the first square, P or our beginning number is placed in this position. To make an up horse move, we move 2 steps and go up, which gives us the position of Q. But there are also other ways of making the same up horse move. Let's see how. We can also move up and go 2 steps towards the right, which will again take us to the same position. Let's try a third way. Let's say we go up and go towards the left, right? Since this is outside our square, it gets wrapped around and comes to the same place. This demonstrates the up horse move. Now let us see the down horse move. If our starting point is the position P, we move 2 steps and go down, giving us the new place for Q. For a left horse move, if P is here, we move left and go down 2 steps. This is a left horse move. Now let us assume we wanted to move left but not go down, but instead go up. Again, we move 1 place left and take 2 steps. Since this is outside our magic square, we will wrap it around and bring it back to the same position. This way you can see how the same move can be made in many ways but will give us the right position. Finally, let's say we want to make the right horse move. From P, we go right and move 2 steps, giving us Q. Let's say instead of going downward, you want to go up. Again, from P, we go right, go 2 steps above in a horse fashion, and this gets wrapped around and comes down to Q. This explains the 4 different types of horse moves which are possible to do in the construction of a square. But sometimes it may not be as straightforward as just placing a number within our magic square. What do we do in those cases? Let's find out. Now let us assume our starting point is P in this box. For an up move, what we do is we go up and make 2 moves, right? Since this is outside the ambit of our magic square, we wrap it around and it comes down to this position. Similarly, for a downward placement, if we start with P here, we go 2 steps to the right and move down. In a left move, with P being in the same place as in the other instances we saw, how will we move towards the left? We go 1 left and make 2 moves. Since this is outside the ambit of our magic square, we wrap it around and this is the place for Q which we find. Finally, to move rightward, with P being in the same position, we move 1 step right and go down 2 places. This gives us the horse move for the right. Now, with clarity on how the horse moves within our square with our starting point fixed, we will try looking at the algorithm which Narayana Pandita has given in his text. Having learnt how the horse moves and seeing the different ways in which it can move inside our magic square, we now come back to our original sequence which we had decided. The sequence is very important because it will be the constituent numbers of the magic square which we construct. So as you can see, we have broken our sequence into 4 subsets, creating S1, S2, S3 and S4. The horse moves that will be considered for obtaining the magic squares are presented in this fashion: H1, H2, H3 and H4. Here you can see, which means 1 to 2, 1, 3, 3, 4 should all be in horse moves to each other. 5 and 6, 5 and 7, 7 and 8 and so on. Like we saw before, the transition between the sets must also be a horse move, which means 1 and 5, 1 and 9, 9 and 13 must also be in horse moves from one another inside our pan magic square. On this slide, you can see the pictorial representation of how these horse moves should look. So, for instance, 1 should be in a horse move to 2. It should also be in a horse move to 3. 4 should be in a horse move to 2 as well as 3. Now, with our sequence and sets correctly in place and the knowledge of horse moves also ready with us, we will try constructing our own pan magic diagonal square. Important thing here when we start is to keep a table of our equivalent horse moves ready, because this table will give us a reference of which number should be in equivalent horse moves to each other. Now let's begin. The first step is we pick a position for 1. Let us say this is the position we pick for the number 1. Since 2 is the next number in our sequence and it must be in an equivalent horse move with 1, we will try seeing where all the placement of 2 is possible. Now if we start from here, we can either place 2 in this particular square. If we go downward, we can place it here. This wraps around and gives us this particular position for the number 2. If we were to go up, we go up, move 2 positions, wrap it around and we get another placement for the number 2. And in a final move, we go down and take a right, which gives us 2. So here you can see these are the 4 possible places where we can place the number 2 using horse moves from 1. For the purpose of our construction, let us pick this place to place the number 2. In the next step, we have to place the number 3 in horse move to 1. Before we move to that particular step, let us remember that we must also write down the move which we have made. So in this case, since we have moved downward to ascertain the position of 2, we will just denote this with the alphabet D. In the next step, we must place 3 in a horse move to 1, as you can see here from our table. So let's try the possibilities of where all the number 3 can go. Again, moving up, we see that the possibility of the number 3 is here. If we were to move to the left, wrap around, this is another possibility where we can place the number 3. Similarly, if we go towards our right, this is one more possibility. So these are 3 possible places in which we can place the number 3 to construct our square. Now, in order to work forward, we will pick one of these positions and move forward from there. Let us say this is the position we pick to place our number 3. In the next step, the number 4 must be placed in an equivalent horse move to number 3. But like we saw before, we also need to find out which step we took, right, for the placement of 3. So each time we make a move to place a digit in a particular column, we write down the nature of the horse move we have made. which is why from 1 to 2 we made a down horse move. In a similar fashion, for placing the number 3, we have used an up horse move, which we will write down here along with our numbers. In the next step, we have to find out where can 4 be placed such that it is a horse move to 3 as well as to 2. As you can see here, this is an ideal place to place our number 4, given that it is in horse move from 3 as well as from the number 2. And hence, we have placed the digit 4 in this location where it is in horse move to both 2 as well as 3. Since this is an up move, we will write and record that move here in our table, and it will be applicable to our other equivalent horse move sets. Now, our first set of our series is complete. Moving on to the next set, which includes 5, 6, 7 and 8 as numbers in the series. We must remember that 5 must be in a horse move from 1. And since we saw from the beginning the only 2 possible places for 5 is either this particular square or this one. So, let us place 5 over here. Then 6. From our table here, we can see that 5 and 6 must be in a horse move to each other as well as equivalent to 1 and 2, which is a D or a down horse move. This will help us figure out the location of the 6 digit on our magic square. So, moving from 5, we go down and place the digit 6 here. The rule of equivalent horse moves states that 5 and 6 must be the same move as 1 and 2, which was a down move. And we will see how we can apply this to find the place for the next digit. So, 6 being our next digit, from 5 we move 2 places and down, and this gives us the location of 6. Moving on to 7, the law of equivalent horse moves tells us that 5 and 7 must be in the same move as 1 and 3, which is an up move from our table. So, we find out that the location of 7 must be, now to position 7, the law of equivalent horse moves tells us that it must be in the same move as 1 and 3, which is an up move. So, starting from the digit 5, we go up and we find a place for 7 here. Similarly, 7 and 8 must be an equivalent move to 3 and 4, which is again an up move. So, going to 7, we go up, make a horse move, and this gives us the location for the digit 8 on our magic square. With our second set complete, now it is time for us to move to our next set, which is 9, 10, 11 and 12. Let's begin by placing the number 9. As we see in our steps column here, 9 must be in a horse move from 1. Now, in our magic square, we can see that all other positions for horse move from 1 are occupied, but this one square, which is where we will place our digit 9. 9 and 10 must be in a, because of the law of equivalent horse moves, must be in a down move. So, moving down and tracing the path, we will see this is where we can place the number 10. 9 and 11 again must be in an up position. So, we will start from 9 and find a place here for the digit 11. 11 and 12 must also be in a horse move with up as the direction. So, from 11 we begin and move, placing the number 12 here. With this particular set complete, we move to our final set to create our magic square and begin with the number 13. As again you can see here, 13 must be in a horse move from 9 as well as 5. So, beginning from 9, we see this is one possibility of placing the number 13, and if we cross check from the number 5, it is also in a horse move in the upward direction. Now, here we can see from our table 13 and 14 must also be in a horse move in the downward direction. So, we go down and we place 14 here. 13 and 15 must also be in a horse move in the up direction. So, let us say from 13 we go up, wrap around and we place 15 over here. Finally, 15 and 16 must also be in a up horse move, which is also the last blank space left on our pan magic square, which is where we place the number 16. So, this way, following this particular method, we are able to construct our very own pan diagonal magic square. You can check your magic square by trying to add the sum across the rows, across columns, across the diagonals as well as across the broken diagonals to see if this is a pan diagonal magic square. The sum in each case should come up to 34, which is the magic sum of this particular square. Now, as you can see that every time we followed a step and did an operation here, we were able to easily fit the numbers inside our magic square. However, sometimes our move may get blocked, in which case we may have to move in the opposite direction. Let us see one more example where we will illustrate this particular idea. With the same series, let us now try constructing one more magic square. Let's say this is the position we fix for 1. For 2, the 4 possibilities we have are these. Let us say we go with this particular option and place the number 2. Here we will log the move which we have made, which in this case has been the down horse move. So, we will put a D over here. In the next step, we have to find the right place for the digit 3 such that it is in a horse move to 1. Out of these 3 possibilities, let us say we pick this one and place the digit 3 over here. Again, as you can see, this was a right horse move. So, we will record it here with our table and put R to denote a right move. From 3, we must move on to 4. 4 must be placed in such a way that it is in a horse move to both 3 as well as 2. So, one possible way we can do this is, let us say we place our 4 here, it is in horse move to 3, it is also in a horse move to 2. And again, now recording the move which we made, it is a down move which we must write down in our table. This completes the first set of numbers in our series. Now moving on to the second set, which is 5, 6, 7 and 8. We see that 5 and 6 must be in a down horse move, same as 1 and 2. As we transition to our next set, we look at the rule which tells us that 5 must be in a horse move from 1. So, from 1, these are 2 possible places where let us pick this particular square and place the number 5. Now, from our table, we find that 5 and 6 must be in the equivalent horse move as 1 and 2, which is down, right? So, starting from 5, we go down and this is where we can place our number 6. Moving on to 7, 5 and 7 must be in the equivalent horse move to 1 and 3, which is a right move. So, starting from 5, we go up and make a right move. However, we find that this move is blocked. When we wrap this around, it is blocked by the digit 1 already placed here. Now, when such a scenario happens where our equivalent move is blocked, we perform the opposite move, which means if we were to suppose to go in the right direction, we will go towards the left. What will that left be? From 5, we go up, take a left and place the digit 7 in this particular column. Now, we also find that our table tells us that 7 and 8 must be in an equivalent horse move as 3 and 4, which is down. So, from 7, let us head downward, make a horse move and place the digit 8 over here, which completes our second set. So, now as we transition to the next set, we see that 9, 10, 11, 12 are the numbers we are dealing with. In the steps you see 9 must be in a horse move from 1. So, if 1 is here, these are the 4 possible places like we saw before, which means this is the only place left where we can place the digit 9. 9 being placed, we see that 9 and 10 must be in an equivalent down horse move. So, from here we try a down horse move, but we are blocked since this place is already occupied. Now, when such a thing happens, we perform the opposite move, which means we go up. Going up, this is the place we will give to the number 10. 9 and 11 must also be in a horse move in the rightward direction. So, let us try placing 11. Can be placed here correctly. 11 and 12 according to our equivalent horse moves table should be in a horse move to each other in a down direction. So, from 11 now we try placing the number 12, but as you can see this is a blocked path. So, we will invert this move and go up, giving us this as the place for the number 12. Now, moving to our next step, we begin with the digit 13, 13, 14, 15 and 16 are the last 4 numbers we must place, and the rule tells us that 13 must be in a horse move from both 9 as well as 5. So, let us try finding a place for 13. If we go this way from 5, we can place 13 here, and with 9 also this criteria qualifies, which gives this as the correct place for 13. Our equivalent horse moves table tells us that 13 and 14 must be placed in a horse move in the down direction. So, let us start. If we were to take this, we realize that we are blocked by the placement of the digit 5. We must invert this move and place 14 here at the top. Next, with 15, we know that 13 and 15 must be in a rightward equivalent horse move. Let us figure that out. So, from 13, we go rightward, but however, here you see we are blocked by the digit 9. We will invert our move and place the digit 15 over here. Finally, for our last number in the series, we know that 15 and 16 must be in a downward move. We take the downward move. Unfortunately, we are blocked by 7 in this direction. So, we will go up and place 16 in the last remaining square of our pan magic. So, here you can see that with this example, we have also learnt how to place our numbers in cases where our equivalent moves are blocked, right? The simple thing that we do is we perform the opposite move, which means if it is up, we go down, if it is left, we go right, and so on. So, I hope that the 2 examples that we took clarified the method as well as the rigor of the Turagagati algorithm by Narayana Pandita. As you saw in both our examples, we fixed the position of the digit 1, like you can see here on the screen, in the top left corner. And you will see, as you delve deeper into magic squares and try out different combinations and constructions yourself, you will see that there are 24 possibilities for a 4x4 pan-diagonal magic square with the fixed position of one element. Like here, you can see on the screen, there are 24 possibilities if we keep the digit 1 fixed in a particular place. But at the same time, we can place this first number in any of the 16 cells. We don't necessarily need to keep it in this particular place, in which case the combinations or the number of possibilities becomes 16 into 24, which is 384. This clearly shows the genius of the algorithmic method which has been given by Narayana Pandita in his text. I am confident to say that this particular method does not have a parallel in other currently existing mathematical traditions. And I hope that magic squares have been of interest to you, and you will go back, watch this video and try many combinations of your own as you find the time. Thank you so much for watching this video. Namaste.